So some of this stuff that we see in section 3.4 about horizontal asymptotes and limits to infinity or at infinity, we learned actually in pre-calc, but we didn't necessarily always put it in this formal calculus notation. So as long as you don't get yourself hung up on the notation of it, we actually already know this stuff, okay? So that being said, let's think about vertical asymptotes, horizontal asymptotes. That's what this lesson is bringing into our graphs. In section 3.3, most of the graphs we were doing, you did not see horizontal or vertical asymptotes because they're going to address it in 3.4. So what does that mean in 3.5? That means in 3.5, they're fair game. We got all that junk pushed together. Okay, so that's why 3.5 becomes one of our hardest sections this year because it's going to blend everything we know about graphs together. Okay, so let's take a look at end behavior. If we have this function, and so you might just want to highlight some stuff, and you've got to be kidding me. No, it's sometimes when the device connects to this, it forgets the pencil. I'll try to remove it. I try to edit that stuff, but okay. So if we look, so you might want to highlight some things, people. If you look at a function like this, we learned back in pre-calc that a horizontal asymptote occurred as a coefficient on the x terms when the x term lead terms match. So our highest power term on top is degree 2. Our highest power term on the bottom is degree 2. So we use the coefficients that are stuck on those two terms to find out where the ends are heading. So that's why the right end, so please note this is the notation for the right side. As our x goes to infinity, where's our function heading? To 1. We can also say the limit as x approaches negative infinity of our function is also heading to 1. That is our left end. And since they match, we can say because both sides are going, well, we don't worry about the both sides for this one. We'll get to that one. I'm sorry. I'm kind of jumping ahead of myself. So the limit to infinity is really just the right end notation. The limit to negative infinity is just the left end notation. What height are we going? And now we're mostly going to be concerned about rational functions. Is it a polynomial over a polynomial? Then it's just a comparison of the powers. It's just a comparison of the powers. So what this says here, as we go from some value a to infinity, if we are heading to a certain height, as our function gets sufficiently, or x gets sufficiently large, if we get closer and closer to that height, that's our limit. So this is just the horizontal asymptote on the right end. This is just the horizontal asymptote on the left end. So we can just blend our information that we have learned from pre-calculus class. We can just blend our information that we learned from pre-calc class. So this is just the notation for the right end. This is notation for the left end. But you have to recognize that's what that means. This means what is the limit as x goes to infinity? They're saying what's the right end doing? If you see what is the limit as x goes to negative infinity, they're really asking you what is the left end doing? Is there a horizontal asymptote? So we learned those horizontal asymptote rules last year. We did not necessarily give it this formal notation. So it's just a matter of blending what we know. So we're going to talk about, remember, if the powers match, we use the coefficients. If the power on the bottom is more, it's going to 0. If the power on the top is more, it's going to go to infinity or negative infinity. So they're just saying that end has some horizontal asymptote if, as we go to the left, we head to that, or as we go to the right. So this one has a left end behavior of L. This one has a left end behavior. So both of these, we would say, has a horizontal asymptote at L. This is the limit as x goes to negative infinity of our function is L. Now, sometimes we have an only a left end or right end horizontal asymptote. You might notice that this right end goes up and this right end goes down. So not the ends don't have to match. So then it becomes is one end doing one thing and the other end doing something else. Yeah, so these ones are both heading to negative infinity. That left end is heading to some height L. The right end doesn't necessarily have to go to that horizontal asymptote. So horizontal asymptotes are a little bit strange. Our function can even cross over a horizontal asymptote. It is just, I can ignore all this and I'm just looking at what is the end behavior. So that's something that's a little different. A vertical asymptote we cannot cross. A horizontal asymptote you might, I've seen some functions where they, you know, they wiggle until they head to that horizontal asymptote. Ones that combine like x's and sines or cosines together, like x squared sine of x, x, you know, sine of x cubed or something of that. Those weird functions will do that. Sometimes the ends will go and squeeze closer to zero. So in this graph, we're just going to break apart what we know. This function, be careful. It's sometimes in their graphs hard to see our x and y axis. So let's make our x and y axis a little bit darker so we can see that a little clearer, okay? And then I'm going to make dashed lines everywhere that I see possible vertical asymptotes, and then I will also mark our horizontal asymptotes. Oh, it sure the heck is. I told you it was hard to see. How about if I put it over there? I wondered why it said 2 right there. Okay, so let's make a little dashed line here. Let's make a little dashed line here. I know I could switch it off, but I'm too lazy to do that right now. Let's make a little dashed line up here and a little dashed line right there. So I've marked that we have a vertical asymptote. We're counting by ones at -1 and at +2. Okay. I have a horizontal asymptote on the left end at y equals 2, and on the right end at y equals 4. Okay. So first I'm just going to really analyze the picture, mark down those things that are occurring, and then I'm going to put it in more formal notation, okay? So it says, find the infinite limits, limits at infinity, and asymptotes for the function. So we found all of our asymptotes. Our vertical asymptotes occur at x equals -1 and x equals 2. So that's the limits that we want to, we will get an infinite limit. So this really matches up with the vertical asymptotes. So let's do those first. So we need to analyze as we approach -1 from the right. We need to look at where we approach -1 from the left. And we need to analyze, do they match at -1? We're going to do the limit as x approaches 2 from the right, 2 from the left, and at 2. So a limit surrounding a vertical asymptote will always have an answer of positive infinity, negative infinity, or does not exist. Okay, so as we approach our vertical asymptotes, we are going to get answers of negative infinity, positive infinity, or not exist. Okay, so let's look as we approach -1 from the right. That's this spot right here. We are going to positive infinity. From the left side, we're going to positive infinity. So both of these answers are positive infinity. And only because they match do we have an answer of positive infinity. Now let's approach 2 from both sides. Let's go to the picture. From the right side, we're going to positive infinity. From the left side, we're going to negative infinity. Let's put those in their proper locations. This is right side going up to positive infinity. Left side's going down to negative infinity. They do not match, so this does not exist. Like any limit, if they don't match, then the limit doesn't exist, even for infinite limits, okay? Now, limits at infinity is just a fancy way of saying, what is your horizontal asymptote going at, okay? Our horizontal asymptotes occurred at 2 and at 4. The left end we write always as x going, the limit as x goes to negative infinity. The right end we always write as the limit as x goes to positive infinity. That's always the notation for left and right. That never switches. If our function is like a parabola on the ends going up, 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 or down, 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 if it's like a cubic, up, 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 down, 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 then we might have an answer of positive and negative infinity if it's just going up, 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 or down, down, down. But the left end and right end for this particular function is heading to a height. So the left end is heading to that height of 2. Our right end is heading to that height of 4. So that is our infinite or limits at infinity. That is our limits at infinity. Positive infinity goes to a height of 4. Negative infinity goes to a height of 2. So we've done everything they've asked us here. The infinite limits are answers of infinity. That happens at a vertical asymptote. Limits at infinity mean what are the horizontal asymptotes. So you just need to know that more formal notation, okay? We know these things because we've been looking at them since probably Algebra 2 and pre-calc last year and stuff. So it's just being more formal about how we write those answers, okay? Does everybody see how we did example 1? Okay, so remember, infinite limits are vertical asymptotes. Limits at infinity are just the ends, so we can call that even the end behavior. Okay, so there's example 1. Now, some things to note. Because of the nature of this function, the left end and the right end of both of those is equal to 0. Think about if you plug in a million, 1 over a million heads to 0. Think if you plug in negative a million, 1 over negative million, super close to 0. It's 0.000001. I mean, just very tiny decimal. And we know from the graph of a rational function that the ends head to 0. So there's a rule we get that if our power is anything bigger than 0, 1 over x to a power anything bigger than 0, we know by default that the ends always head to 0. So 1 over x to the half, the ends head to 0. 1 over x to the fourth, the ends head to 0. Any positive power bigger than 0 will always result with the end behavior heading to 0. So this is just saying that the ends head to 0, or our horizontal asymptotes is y equals 0. So that really eliminates the question of what's happening. We know that there's a horizontal asymptote of 0 for this function. As long as we have it lifted up or down, that will always happen. If you have a plus number on the outside, that will lift it up or down depending if it's positive or negative. So if they ask me to evaluate this function, I am going to say, oh, that's just asking me the ends. And I think I summarized the rules on the next page. But the rules basically say if you have a higher power lead term in the top, higher degree in the top, you are going to head to either in positive infinity or negative infinity. If the powers match, then the limit, we'll just call this function f. As we approach infinity, we always get to use the lead term coefficients. It's heading to 3/5. Now, why is that? Well, let's say, again, use that, let's plug in 1,000,000. If you take 3 times 1,000,000 squared, plus some stuff that's much smaller than that, and you take 5 times 1,000,000 squared, it really just becomes 3,000,000 squared over 5,000,000 squared. It doesn't, the other stuff doesn't matter. Let's think of money. If you have 3 times 1,000,000 squared in your bank account, that is 12 zeros with a 3 on front. If somebody gives you or takes away $1 million from your bank account, do you care? Does it do diddly squat to your bank account? No, not really. I mean, it does something, of course, but it doesn't affect your overall wealth. That's why when Elon Musk was giving away $1 million to people that registered to vote in Pennsylvania, they found it was illegal and he stopped. But when he was trying to do that, he's a billionaire. $1 million to him is like $10 to us. Doesn't mean much, you know. Yes, depending. Of course, that's all relative, isn't it? Okay, so the rules of asymptotes. Let's first talk about horizontal asymptotes. If the degree of the numerator is greater than the degree of the denominator, there is none because the ends are always going to plus or minus infinity. Because then the higher power that's in the top wins. It is overpowering all the lower power stuff that's in the denominator. If the numerator is bigger than the, less than the denominator, it's always going to go to y equals 0 because now the denominator wins. But if they match, they're of equal importance. So you just use that lead term coefficient. So if the lead term coefficient on top is a and the lead term coefficient on the bottom is b, it's just going to end up being a over b. We did those rules last year. So remember, these are limits to plus or minus infinity. Horizontal asymptotes are limits heading to infinity, okay? If the top matches, it wins, so it can go as high or low as it wants. If the bottom matches, if the bottom is higher, they always head to 0. But if the degrees match, use the ratio of their front coefficients, the lead term coefficients. So you could even add the word here, lead term. Okay. So that's our horizontal asymptote rules. Remember, horizontal asymptote is always y equals some number. Unless, of course, the degree in the numerator is more. Or if it's a polynomial, which uses that even odd sort of rule. If the degree of the numerator is less than the degree of the denominator wins, it's always going to head to 0 because we're dividing by something bigger than what we started with. But if the degree of the numerator and denominator match, then use the ratio of the lead term coefficients. Now, vertical asymptotes, you have to ask yourself, for rational functions, where does the function not exist? But don't forget there might be a hole there. Remember, holes exist where a factor on top matches factor on bottom, like the problem from the 5-minute check. We were able to plug a hole. It wasn't a vertical asymptote. So it's where the denominator equals 0 after it has been reduced. Remember, vertical asymptotes is some x equals, we'll call it a. So we're really looking as x approaches a from the right or from the left. So we are approaching that asymptote, and we're going to get answers. Your answer are plus or minus infinity, some positive infinity, negative infinity, or possibly does not exist if they go in opposite directions. So remember, horizontal asymptotes are limits at infinity. These are infinite limits. The answer is in infinity. Okay, so just so you know the language of it. I know that's a lot to write, but you know, writing sometimes helps it stick in your brain a little bit. I usually don't have you write a lot, but I need these rules to get stuck in your brain. That's why I post my videos. You can rewatch and not write, you know. I've had some people do the opposite. They pay attention in class, watch it, but then go home and actually write it out. You know, freeze frame the video and write it out. So you got to find what works for you. Yeah. You're okay. Yeah, I did throw a little bit extra info in there. Yeah, it says infinite limits of micros writing.
This is kind of like the same thing we learned.
We already know this stuff. It should be a review of pre-calc information, but now we're putting it a little more formally. It's just knowing, hey, they asked me this. Oh, that's a horizontal asymptote. Oh, that's a vertical asymptote. Yeah. Okay. I know. So let's talk about the horizontal and vertical asymptotes of this graph. If it is in fully factored form, then the vertical asymptote occurs when the denominator is equal to 0. So there is a vertical asymptote at 5/3. So as we approach a value of 5/3, we will either go and skim it up to positive infinity or skim it down to negative infinity. The limit as we approach 5/3 from the left and right will both have answers of either positive or negative infinity. Okay. Now let's talk about the horizontal asymptotes. The lead term on top is kind of like the square root of 2x squared, which is really the square root of 2 times x. The lead term on the bottom is 3x. Don't they match? Technically, they kind of match. So the horizontal asymptote occurs when y equals the coefficient on top over the coefficient on the bottom. So both ends, well, maybe not. Yeah, that will be both. Both ends head to square root of 2 over 3. So that would be a limit to infinity. So we already know that the limit as x approaches both positive and negative infinity of our function will head to square root of 2 over 3. Okay. So how can we check our work? Desmos. That's it. Okay. So the square root of 2x squared plus 1, make sure that stays under your square root, divided by, 3x minus 5. Let me show you how to check your work. Put in the horizontal asymptote. Y equals the square root of 2 divided by 3. See, both ends, what are they doing? They're heading to that value. One end will get a little lower first and kind of come back up. Okay. So if you look at this end, it takes a little while, but it will head there. It will, yeah. Okay. No, I don't believe so. It is under, yeah, but I don't believe so. Yeah, I'll contemplate that more. Well, oh, you are so smart. Okay. This is a case that the top is always positive, right? Because it's under a square root. The original version, your brain is amazing. The original version, it squares the top even when we go to negative infinity. So this goes to a positive always, but on the left side, this will go to a negative. So I lied. Both ends do not head. This is plus or minus. And I'm sorry, because that squared messed that up. So our right end heads to square root of 2 over 3. Our left end heads to negative square root of 2 over 3. And when you plug in a negative, what happens? Well, the top squared it first before it square rooted it, and the bottom didn't, so it stayed a negative. It's a weird case. Thank you. I like that. Okay, so you found that. Thank you. Wait, that's not what I want. So then if you put in the vertical asymptote, let's go back. The vertical asymptote is x equals 5/3, and it should show up, and it does. It splits that right down the middle. We could say that the limit as x approaches it from the left is negative, and the right is positive infinity. So we could even now add the limits. The limit as we approach it from the left is negative infinity. From the right is positive infinity. So the limit as we approach 5/3 is a does not exister because of the fact that they don't match. They're not both going swoop up or swoop down. Okay. Thank you for helping me with that one. Okay. We are only checking here the limit to infinity. This one is kind of a weird one, but we only are plugging in positive numbers, so it won't be so bad. What I think about the fact is that big numbers, that's going to act like x. So the plus 1 won't affect our answer, so it should head to 0. It should head to 0. Again, go into Desmos, because remember, that's just a horizontal asymptote rule. So if we do the square root of x squared plus 1, and then we do minus x, you'll see that the left end is clearly heading to 0. Oh, really? I like that. Sometimes that's not a bad idea. Your uh, your Desmos thinking is just such a neat thing because um, what he was saying is if you put in, let's say, f of 1,000, see how, look how close to zero it is. Put in a million. Yeah, as soon as you get to 100 million, it says it's so close to zero, I can't even tell you how close to zero it is. So that, remember, is just what is the right end doing. That is what is the right end doing. And so I think of big numbers, and you can always just, if you have a calculator, plug in 1,000, plug in a million. What's it close to? It's going to say 0.0000 something on your calculator. Pick zero, you know. So plugging in numbers is helpful. We haven't talked much about ease, but we learned how to graph exponentials last year. We are going to talk about some exponential stuff later on. The left end, see how this is the left end, does have a horizontal asymptote at zero. The right end goes to infinity because it's exponentially growing. Exponential decays, the other end, the right end, heads to zero. So we are going to continue these last problems tomorrow. It's looking like we are just going to focus on 3-4 this week and then 3-5 next week. Okay. Continue lesson 3.4. Anytime you see a limit, you need to kind of try to first think about what they're asking you. So when they're doing this limit as x approaches zero from the left, we can assume something funky is happening at zero, okay? So think about the fact that if you try to do direct substitution, you get e to the 1 over 0, which is undefined. So that tells us something funky is happening, okay? So let's do a little trick. What you can do is let's think of a number that is to the left of 0. So a very small number to the left of 0. Let's pick something like negative 0.01. Okay. Let's plug it in to help us figure out what is happening. Okay. So if we do e to the power of 1 over negative 0.01, let me tell you what we get here. So we get e to the power of 1 divided by negative 0.001. My calculator is so, it's that many decimal places that they just called this 0. It's such a small number that they just recognize it, well, your head to 0. So they kind of give it to you. So this limit is 0 from the left. Now let's do another trick. Let's plug in something to the right. Let's see what's happening there. So a number that's approaching 0 from the right, this time let's plug in positive 0.01. If you plug in positive 0.01, it is such a large number that it can't calculate it the opposite way. So that side's going to positive infinity. It's a weird looking graph of this function. If you try to graph, I don't even know where to find e. Can somebody help me? Just pick an e and it'll do it. Okay. To a power of 1 over x. It's a strange looking graph. Think about as we approach 0 from the left, we're heading to 0. But if we approach 0 from the right, we are heading indeed to infinity. So even if you're unsure of what the graph is doing, feel free to plug in a very small number to the left of what you're getting or to the right. You can use a numerical value to help guide you when it's a funky function. Okay, okay, the funky function. Let's look at this one. Now, the sine function, I hope that you realize that our sine function continues that pattern to the left and to the right. It's called an oscillating function. So this is one where as we keep going out to infinity, we keep oscillating between +1 and -1. We don't pinpoint a location, so this does not exist. So that happens often with our trig functions. What value do we stop at? You know, what value would we pick if we went way, way out in either direction? And so because of that, you know, you have to really, you know, try to say, well, it's not going to a particular height. Sometimes it's up at +1, sometimes it's down at -1. Sometimes it's anywhere in between. So because of that, you know, we can't really specify. So sometimes you have to use logic and what you know about the graph of something. Okay. Now here we can use what we know about the end behavior of a cubic. We can just use logic. We know that a cubic looks like this. This is just notation for the right end. This is just notation for the left end. So the limit as x approaches infinity is saying, what height are you going on the right end? I am going to positive infinity. This notation is saying, what am I doing on the left end? We're going to negative infinity. So some of the things we know about the lead term of polynomials should help us answer those limits at infinity just based upon the knowledge of stuff we learned in pre-calculus. It shouldn't be some magical thing. It should be pretty straightforward. Excuse me. Everybody good with that? Wouldn't it be great if they're all like that? So that leads us to an actual polynomial. The end behavior of a polynomial is determined by its lead term. The lead term of this is x squared. So it's going to act like a square on the ends. Yeah, it does have some bumps in the middle. I mean, it does have the you know, parabola action going on there, but the ends are still going to act like an x squared. So this is just saying, what is the right end doing? So the limit as x approaches infinity of x squared minus x is just going to be positive infinity because I know the left end and the right end are heading up. So I shouldn't have to think about it. It's just knowing what the notation is a shorthand for. That is the right end. What is it doing? We know what a polynomial does on the ends based upon that lead term. Now here, when it's a rational function where you have a polynomial in your numerator and denominator, you do have to use the lead term, the highest power in both. So the lead term on top is an x squared. The lead term at bottom is a negative x. If I were just to isolate those large things, so if I kind of throw out the extra stuff and only focus on our lead things, this is going to act more like a negative x than anything else on the ends. We know what a negative x does. It's just a line with a slope of -1. So we know that the left end is going up and the right end is going down. This means that the limit as x approaches infinity of x squared plus x over 3 minus x, when it gets really, really large, is going to act like the line negative x. And so the right end is going down. So you got to compare the powers on top and bottom. If the top power is more, how much more and why? If the bottom power is more, you know that it's going to 0 on the ends because that bottom power is going to divide off and give you the most stuff at the bottom. If the top and bottom match, it's going to always head to that ratio of the coefficients. Okay, so you have to know what they're asking, and then you need to go from there, okay? So hopefully this notation, it can't throw you. You know this stuff. You have to just learn what is that notation telling you, because you do know this stuff, okay? Now, let's use what we know about polynomial functions in factored form. Let's put together everything we learned last year and this year. I'm not going to be super hyper about the concavity and stuff, because taking the derivative of that, because it's a product of a product, we're not going to worry about that. But let's do a rough sketch of this polynomial based upon what we know, okay? The zeros occur where x minus 2 equals 0, which is 2. But because of that even power on that factor, there will be a bounce. X plus 1 equals 0 at negative 1. There's an odd power on that, so we're just going to go through it. X minus 1 equals 0 at 1. There's a one of them that's an odd power. We're going to have to go through that. Okay. The y-intercept, I'm going to write it in function notation. You just plug in 0. So it's going to be negative 2 to the 4th, 1 to the 3rd, and negative 1, which is an answer of 16, negative 16. Let's talk about the end behavior that limits to infinity. Our left end, well, let's do our lead term first. If we pull out all the x's, and if there were any constants out there, we would get x to the 4th times x to the 3rd times x for a total of 8 x's. Okay. So our right end, which is our limit to infinity, is going up. Our left end, which is our limit as x approaches negative infinity of our function, is also going up. Okay. So we have everything we need in order to graph that pretty seamlessly, pretty nicely, okay? So let's put all of our information together. On my x-axis, I'm going to count every 2 spaces as a whole, just to split it up a little bit. I need a y-intercept of negative 16. So I'm going to count by 4s. Every other one, so technically 2s. But I think I'll get to 16 that way. Okay. When graphing a polynomial or a factored form polynomial, put on your zeros. So we have zeros at 2, negative 1, and 1. Then put on our ends. Our left end goes up, our right end goes up. Put on your y-intercept, and that will help you to make your bounces and your throughs. Now we're going through the point positive 1 and negative 1, but we have a bounce at 2. So we have to go through or down through that one, through, bounce. And so that is our graph for example 11. And we learned all that stuff last year. We did that pretty extensively. So hopefully that is a reminder, and that helped you remember how that stuff worked and how that notation fits with this section. Okay. 3-4 is just kind of taking the stuff we learned in pre-calc and putting the more calculus notation with it, but you actually know this stuff, okay? This is the precise definition of a limit. We're not going to do anything with it. If you would take a more theoretical calculus in your future or do something called real analysis, we use this epsilon notation. And it just basically says is as we go to infinity, we are getting closer and closer to that limit value by a measure of epsilon. So the function, the distance between the function and our limit is getting smaller and smaller and smaller. So that's what that notation means. But I just wanted to just see that precise definition, that epsilon notation. And there's some really cool Desmos things where they put the epsilon in and it slides and does some neat stuff. I think it exists out there. Just put precise definition of the precise definition of the limit, and you might get a template that's out there that's kind of cool. So that leads us to homework. So today and tomorrow, I want you to be working on your 4-4, okay? And it's the odds that you see there. Or not 4-4, I'm sorry. I didn't change that, did I? It used to be 4-4. With our book, it's 3-4. Please work on this for the rest of class and work on it tomorrow. The homework is due, I believe, on Sunday, but I'll check to make sure that's the case. And then next week, we're going to focus on 3-5 at the beginning of the week. But that means Friday, you're having a 3-5 quiz that covers all of this stuff together. Graphing, concavity, inflection points, and behavior, all that stuff. Okay? There you go. No, you'll be okay. We'll practice enough next week. So 3-5 will feel very repetitive. It's 3-4 with just some of these